Good afternoon, everyone. Today, the Admirals seminar has the great pleasure of welcoming Professor Nagu Daraboina. Professor Daraboina completed his PhD at the University of British Columbia and his master's degree at the Indian Institute of Science. He is currently an associate professor at the Russell School of Chemical Engineering at the University of Tulsa, where he is also the associate director of the Tulsa University Paraffin Deposition Project. His research focuses on flow assurance, carbon capture, storage, and utilization, productive water desalination, and energy recovery. His team has pioneered experimental methods to advance water treatment and carbon capture using hydrate technology. In 2022, Professor Daraboina was the top two most cited scientists worldwide. Over the course of his academic career, he was honored with multiple awards, including the 2021 Rising Star in Energy Research from Energy Fields, the 2023 Donald W. Davidson Award for Gas Hydrate Research, and the 2023 University of Tulsa College of Engineering and Natural Science Leslie Schmid Outstanding Research Award. So once again, welcome Professor Daraboina. Thank you so much for accepting our invitation. It's a pleasure to have you here with us. Please feel free to start your presentation.
Good, I'll continue. Okay. These topics may appear unrelated at first glance, but both are unified by a common thread, the strategic use of thermodynamic understanding to guide better decisions in a complex industrial systems. The first topic I'm going to talk today about how we use thermodynamics to combat wax deposition problem in oil and gas pipelines. And second topic, I'll would like to, this is the recent topics we are working in last couple of years, how to manage and how thermodynamics help us to develop a new processes. So these two topics are completely different, but they're all, they both tied up with the common thread called thermodynamics. The goal is, today's goal is to illustrate how subtle but targeted thermodynamic adjustments can often outperform radical overhauls or ad hoc solutions we have. Already, like the organization introduced me, so I won't spend much time about talking about me. So let's go further. Before I begin, I want to emphasize that the work I'm presenting, much of the research was carried out by a dedicated team of graduate students and postdoctoral fellows, supported by a funding from U.S. Department of Energy. So I'm incredibly grateful for their hard work and support. With being said, like let's dive into the first topic. Despite rising the global energy demand, fossil fuels still remain a dominant dominant today. With the daily oil production, oil could last around 50 or more years with the current reserves. This highlights the need to explore harsher environments such as deep oceans. However, transporting oil from a remote offshore locations poses major challenges. The flow assurance is a discipline focused on ensuring the safe, reliable, and efficient flow of oil and gas from the reservoir to the processing facilities, basically. It involves identifying, preventing, and managing issues that can disrupt or block the flow within the pipeline or any production systems. These issues are further classified into fluid-based and flow-based. Fluid-based are problems caused by the properties and the behavior of the fluids being transported, such as the formation of hydrates, wax, and asphaltenes. Flow-based issues are challenges related to the flow dynamics itself, like slugging, pressure drop, or corrosion. One of the University of Tulsa's most notable contribution is through joint industrial projects, particularly in the field of flow assurance. Since the 1980s, the university has hosted several major oil and gas joint industrial projects and bringing together academia and industry to solve complex flow-related challenges in production and transportation. Um, these JIPs have positioned the University of Tulsa as a global leader in oil and gas research, particularly in multi-phase flow, hydrate, and wax deposition studies. But today, particularly, want to focus on wax deposition. In the subsea conditions, the hydrocarbons is exposed to a very cold environment. As the produced fluid reaches and goes below wax appearance temperature, what we call VAT, the wax will start precipitate out and deposit on the pipe walls over time. This deposition can inhibit, even completely restrict the flow and resulting in decreased production and increased cost and even complete facility shutdowns in some cases. So now I would like to explain how University of Tulsa and the oil and gas industry work together to solve this flow assurance issue of the wax deposition. It starts with generally companies evaluate their oil assets, looking how much oil they can have, its quality, and how we can analysis to determine it's worth investing in a particular project. Then we began running small-scale experiments in labs using using tools like gas chromatography or rheometer, small gas to understand how it behaves under different conditions. This step, what we call the benchmarking. If the results look good, we move on to the larger experiments using the flow loops, and then flow loops that better represents actual pipeline systems. From this, we develop a detailed models to predict issues like wax buildup and flow blockages. These models are then used in the flow assurance software, which helps simulate what would happen in the field. After this, industry move into the field testing, where they apply possible solution to the real world conditions and they gather the feedback. So the two sides, both industry and TU, exchange share constantly the information. The industry provides real data and feedback, while we refine their models and improve the tools. One of the key deliverables industry expect from us is the practical simulation tool that can be used directly in the field. Okay, that's you can see the interface here. Here is the simulation framework by setting up initial time and input parameters such as geometry, boundary conditions, and the number of pipes. The core of the simulation involves looping through each pipe section, where physical processes are computed using four main modules: thermodynamic, hydrodynamic, heat transfer, and mass transfer modules. These modules interact iteratively to reflect a real-time behavior. After updating the conditions at each time step, the loop continues until the final simulation time reached here. This modular and iterative approach allows for flexible and accurate and scalable modeling field scale systems. Here today, I would like to explain how the thermodynamic module really play a role in wax deposition simulator. So to accurately predict wax behavior in the oil and gas production system, it allows us to determine the wax appearance temperature. Here, this is the precipitation curve. So x-axis is the temperature, and y-axis is the wax percentage precipitating out of the oil. As you cool down, at some point of the inorganic compounds, paraffinic compounds, which are dissolved in the oil, are no longer soluble, and they are out. And the first crystal formation precipitate is what WT is very important for a wax deposition modeling. As well as the amount and composition of wax under varying temperature pressure conditions also can be predicted through the curvature here, along with the temperature. So if you know the pipeline temperature, we can also predict how much actually wax is coming out, and then its composition. So these two are very important thermodynamic properties we want before we even go to the wax deposition modeling. Um, the most widely accepted wax deposition model since 2000 is the film mass transfer theory. This model assumes this model assumes all the soluble wax molecules reach the mass transfer boundary layer and start precipitating out and then contribute to the deposit. Here, thermodynamics provide very important information for the model called boundary conditions, okay, which where actually the wax deposition starts. So the temperature is supposed to be below WAT, otherwise the wax deposition doesn't start. And once it starts, the precipitation curve is what dictates how much it's actually precipitating out and depositing. However, how do we verify this model predictions before the field trials? So we need an experimental data. So, but wax deposition, because wax behavior is highly sensitive to temperature, flow conditions, and composition. So reproducing these conditions in the lab with accuracy and consistency is difficult. Measurements like wax thickness, deposition rate are also very hard to capture without disturbing the system. And these tests often take very long time. At Tulsa University, we have overcome these challenges by building custom experimental setups like full-scale flow loops designed to specifically wax studies, and we have developed advanced measurement techniques and standardized testing protocols. So over the years, we have built one of the most comprehensive flow assurance database in the world, which supports both research and industry. Here I am showing the videos. Here I'm showing some examples of wax deposition. In the flow loop, wax deposit thickness can also be estimated indirectly using the pressure drop method I'm showing here. A wax accumulates on the pipe wall, the effective internal diameter decreases, causing an increase in pressure drop across the test section. By comparing the measured pressure drop during the experiments with the baseline is, in this case, is clean pipe. So we can back calculate wax layer thickness. This method is non-invasive and very useful for the real-time monitoring. Also, we collect the deposit after each experiment as shown in these videos here. And then wax content and carbon number distribution will be determined using gas chromatography or differential scanning telemetry. As you can clearly see here in this video, this experiment is conducted at RLS number 12,500 and around 4 hours, 12 hours, 24 hours of wax deposition timeline. As you clearly see from the video itself, the wax hardness is increasing as the time increases, and which we can also clearly observe in high temperature gas chromatography. As you see from C35 to C45, the carbon number distribution is increasing drastically from 4 hours to 24 hours. So this is a sample of experiments, but we collect different crude oils, different operating conditions, different pipe sizes. So we have a comprehensive database. This is a single phase wax deposition experiments, but we also specialize to collect wax deposition video of stratified flow and stratified wavy flow, and the wax deposition was strongly correlated with flow pattern too. Under stratified flow, a deposit formed at the bottom of the pipe, like a crescent shape. However, in stratified smooth flow or in slug flow, it is more or less uniform, and then even though there is more wax deposits in the bottom, the wax covers entire pipeline. This is because in stratified wavy and slug flow, the film thickness, it will always wet the deposit pipe wall, always wet the pipe wall, and it's prone to the wax deposition phenomenon. So this is how we collect the information with the specially designed flow loops. So we consolidated several hundreds of experimental deposition data points using these flow loops under a wide range of operating conditions, fluid types, and durations. You accepted a wax deposition model, and we have an extensive amount of experimental data. So this comprehensive database was used to validate existing deposition models implemented in our simulator, basically. As illustrated here, it is a sample result I'm showing. These are two different curves. As you see here, prediction error is quite high compared to the actual experimental result. In some cases, it is even from 100 conditions. So basically, the models are over predicting the experimental result. So why it has to over predict? Because accurate wax deposition is very important. Otherwise, you are over predicting the wax deposition in the pipeline, and you're wasting money unnecessarily by injecting the chemicals or heating the pipeline, even though there is not much wax deposition at a particular point. So it's very important to predict the wax deposition accurately. So we went back to the basics, and we saw there is only three ways we can incur the errors. So measurement and correlation uncertainty pose significant challenges to model validation. However, their impact can be mitigated by careful sensitivity analysis and the high quality data from repetitive measurements and quantification of uncertainty in measurement. So we are doing this very diligently, but governing mechanism of wax deposition is not fully understood. It's only assumed, and nobody proved yet, that all the wax deposition happening from the dissolved wax and come to the mass transfer boundary layer and deposit. That is a hypothesis, and then the model was developed based on hypothesis, but there is no verification. So the underlying physics and dominant mechanism of wax deposition, especially under dynamic and multi-phase flow conditions, is still under active research. This gap might contribute significantly to the large errors observed in the model predictions. As I showed you in the previous slides, can be more than 100 to 300%. So what we observe, we cannot replicate the field case situations in the lab, definitely, because field case is around 16 to 20 inch pipe, and it's impossible to do those experiments directly in the lab, even though with pilot scale flow loops. The flow loops we use like around 3 inch, maybe 6 inch. But also the existing models are not able to predict this phenomena properly. So we have to better understand the underlying mechanism of wax deposition. We decided to think outside the box and take a novel experimental approach to observe the mechanism of the wax deposition itself, instead of simply doing wax deposition experiments in a closed pipeline. So far the data is collected in the closed pipeline. So we developed a dynamic flow loop system that allow us directly to observe wax formation on the pipe wall under controlled operating conditions. So using this dynamic visual flow loop, we conducted several experiments. Through a series of experiments conducted across varying temperatures, flow rates, wax concentrations, we captured a valuable visual data that reveals very interesting insights. One key here, I'm showing the video of how one of the sample video how the wax crystal can be formed on the pipeline wall. One key observation emerged when we compared the visual evidence of wax crystal formation with the calculated mass transfer boundary layer in the existing theory. We consistently saw wax crystals forming above the predicted mass transfer boundary layer. This observation provides a clear explanation for why existing theories tend to overpredict wax deposition rates. The models typically assume that all soluble wax molecules that reach the mass transfer boundary layer precipitate and deposit on the wall. However, our findings shows that significant portion of wax actually precipitate out above mass transfer boundary layer and does not contribute directly to the deposition, as you see clearly. So the real challenge becomes how can we correct this theoretical over prediction and improve the accuracy of our deposition model. The answer lies in the information that is already available to us, as called precipitation curve. We are using it. If you know the precipitation curve and if we know the radial temperature profile in the pipeline at any point, by analyzing this curve at that profile, we can estimate in real time how much wax is precipitating out above the mass transfer boundary layer. So incorporating this thermodynamic insight into our simulation model allows us to isolate and subtract the non-depositing portion of the wax from the total and correcting the flaw of the original theory. Instead of developing the new theory, we are actually we are understanding the theory and correcting the theory already available. That is precisely what we implemented in our simulator by integrating the precipitation profile with the transport model. We significantly reduced the error. You can clearly see here the errors are considerably significantly reduced in the deposit thickness and then also hardness. These results clearly show how a deeper understanding of wax behavior coupled with smart use of existing thermodynamic data can dramatically improve the accuracy of wax deposition prediction. And we published this model in 2022, a series of publications. The original theory was published in 2000, so it took almost like more than 2 decades to improve the model, even though all the information is available to us. I also want to mention some of the other thermodynamic parameters. Usually in wax deposition, pressure is often neglected in wax deposition modeling, especially in simplified and early stages. However, pressure can play an important role. Here you can clearly see the relationship between the pressure and WAT in a methane-containing system is non-monotonic. Pressure affects the solubility of the wax components by controlling how much light hydrocarbons like methane remains in the fluid. So this directly alters the WAT, which is critical for predicting where and when the wax begins to precipitate. In offshore ultra-deep water long pipelines, pressures range from probably 100 to like a few hundred bars. So neglecting pressure leads to a significant errors in WAT prediction and deposition rate. So these are the experiments we conducted in the lab at different pressures. So we conducted the pressure experiments until 900 bar using high pressure differential scanning calorimetry, and we observed that the WAT difference is close to 10-degree difference with pressure. So by knowing this, we conducted some simulations. As you see here is a 25-kilometer pipeline. And we tracked the interface temperature, how it is changing from almost like 45 degrees to the seafloor temperature. And then, as you see here, wax deposition starts at different points along the pipe. It's even the few thousand meters difference. That's quite a lot, depending on the pressure. So the pressure affects both where the wax forms and how much deposit and at what point. And it should not be ignored in the modeling because all the mitigation strategies like injecting chemicals or increasing the temperature should know this position very well. Few thousand meters of heating pipeline costs a lot of money. So this kind of data is very useful, and simple thermodynamic data, how pressure affects the WAT, can give you better understanding of this phenomenon. Also, interestingly, one more important factor we observed, we conducted experiments with different pressures and collected the deposit sample itself. And then that deposit sample we analyzed. WAT is wax appearance temperature, WDT is wax dissolving temperature. As you see here, with the pressure, this temperature required to completely dissolve the wax is decreasing. That means at higher pressures, if you have a deposit formed, then you no need to increase the temperature of the pipeline to um, too high to dissolve that wax. That means that this is because it may be forming a harder deposit at high pressure. So this information is very useful. Otherwise, you're not going to increase the targeted temperature properly, and then you still have some residual wax. So as you see here, small understanding about thermodynamic data can increase the actual pipeline uh, wax prediction quite well. So, summary of the first topic is that thermodynamics tracks how pressure changes alter the phase behavior and how it affects the wax solubility and likelihood of the deposition in pipeline. Uh, Thermodynamic data and models aid in designing proper mitigating strategies. So, estimating just how much wax is forming above mass transfer boundary layer from the precipitation curve increases our prediction capabilities quite high. All these things we are able to achieve by our integrated approach through with the industry partners. So I always say more integrated approach is needed for flow assurance solutions rather than keeping it close. So we should work together to get an innovative solutions. With this, I will conclude the first topic, and I think we are good with the time. So let's shift gears to the produced water management. This project basically we got from Department of Energy 2 years ago. There is a reason why we went in this direction. I will explain that. So here in this topic, I will give how we are using thermodynamics as a part of the process development. Uh, what is produced water? Produced water, also known as formation water, is nothing but is naturally occurring water brought to the surface during oil and gas extraction. It's becoming the largest waste stream associated with oil and gas production. Uh, United States produces a massive amount of produced water annually, with estimates ranging from 20 to 25 billion barrels. This sheer volume and complex composition of produced water pose a significant challenge for its management. As you see here, produced water is a heterogeneous mixture that includes hydrocarbons, heavy metals, suspended solids, and some chemicals, what we use for during the drilling and production. So it also often has a high salinity. Total dissolved solids are approximately goes from 100,000 ppm to 400,000 ppm, which is very high compared to the seawater, and can be toxic. And in some sites, it can be radioactive, depending on the reservoir. The composition varies widely by location and over time in the same well. So making proper treatment and disposal can be more challenging due to this ever-changing composition. In Oklahoma, Tulsa University is in Oklahoma State, and in Oklahoma State, we are the significant producer of produced water, ranking almost among the top 5 states of states for this byproduct in the United States. So what is the problem if you are producing a lot of water? So Oklahoma has experienced increased seismicity, and this is the data I'm showing here. There are small earthquakes from 1985 to now. You see how many earthquakes are there, and these are linked to the injection of produced water from oil and gas operations into deep disposal wells. The high pressure fluid injections with high salinity out of the subsurface stresses, potentially targeting the faults. So Oklahoma has implemented regulations and explores innovative solutions for recycling and treating produced water for various uses. So the goal is to move towards a more sustainable approach to produced water management. including treating, reusing this water to valuable as a valuable resource, while minimizing the environmental impact. So that's where we started. So we started looking into existing technologies and their flaws, and we come up with a bunch of points like what are the requirements for novel technology if you want to develop our next generation technology, what we call. So we're exploring few. One of them are like clathrate hydrate desalination, which is a proven technology for seawater desalination. But can clathrate hydrate based desalination offer a breakthrough solution for this produced water management? That's what we are looking into this project. So what is a wax, clathrate? Sorry, not wax. Clathrate hydrate desalination. Hydrate desalination leverages gas hydrate formation to separate pure water from saline sources. When gas hydrates forms, they trap water molecules in a crystalline structure, excluding the salts and impurities. So after separation and dissociating, we can obtain a fresh water. And this technique offer a promising alternative for energy efficient and selective desalination, especially for produced water. As you see in this animation, when the gas is dissolved, the clathrate structures are forming, but they are not forming with salts. And if we separate these structures, we can clearly get the clean water. So commercializing clathrate hydrate-based desalination demands a structured multi-level evaluation approach. At the outmost layer is a life cycle assessment. So that's one of the requirement. So this LCA is essential to assess the environmental impacts of the process from raw material extraction through the operation to final disposal. However, the conducting meaningful LCA depends on having accurate data on energy consumption, material input, and process cost, which we call the TEA, techno-economic analysis. TEA evaluates the financial feasibility of the system by estimating the capital expenditure, operating costs, energy demands, and water recovery efficiency. This economic assessment in turn rely on understanding some system kinetics. What is the rate of hydrate formation, the rate of dissociation, which also influence the reactor sizing, throughput, overall system design. This kinetic performance often process that define its productivity and operation efficiency, but the kinetic models are rooted in a solid grasp of thermodynamics. Thermodynamics determines the fundamental limits of hydrate formation, identifying the pressure, temperature conditions under which hydrates are stable or not. At the heart of entire framework is thermodynamics. So, in a nutshell, if you want to perform LCA, we need TEA. If you want to perform TEA, we need a kinetic information data. But if you want to have a good kinetic data, you need to have thermodynamic data. So thermodynamics is a core of the entire commercialization process in this scenario. So we conducted this whole project started 2 years ago, and we started conducting some experiments to get the hydrate equilibrium data, phase equilibrium data with the different salts. The gas hydrate phase boundary basically shifts to higher pressures and lower temperatures as salinity increases. This effectively narrows the hydrate stability region. High salt concentrations lowers the water activity in the system, we all know that, which in turn depresses the temperature. This means that at a given pressure, hydrates form at lower temperature compared to more than 10 degrees in this case. So it's very important to understand this. We have lots of data available for seawater. However, produced water is more potent to reduce the operating region quite low compared to the seawater. So it's very important to understand this phase boundary change with the different salts. So we conducted lots of experiments with the different salts. A comprehensive database, close to 500 data points for hydrogen beam was created for a single and binary and several different producer water composition for various promoters. This database promoter is nothing but gas component we use or liquid component we use to form the hydrate. In boundary to implement hydrate-based desalination. However, just having data itself is not good because produced water composition is continuously changing with the geographical locations. Even within the same location, it is continuously changing with the production time and age of the well. So it is important to have a real-time prediction tool with water composition and type of activity sim. This is a simulator we are developing. This is not just a simulator. This is not a simulator, just not about formation. It provides a comprehensive. I'm not going to go too much details about how we are modeling it, but I will give you that a little bit how the simulator works. The presence of salts in water affects the thermodynamic conditions of hydrate formation by altering the basic viscosity of the liquid phase. So dissolved salt ions form hydration cells, binding the water molecules and thereby reducing the amount of free water available for hydrate formation. This reduces the free water leads to the decrease in water activity, the charge size and the hydration strength of different salts. So thermodynamically, this makes it more difficult to form hydrates and saline brines than pure water. To capture this effects in modeling, activity coefficient models were used like Debye-Hackel equation along with modified Davis equation or some in-house developed equations are used to accurately predict the reduction in water activity due to salt presence. I also worked with Denmark Technical University for almost 3.5 years as a postdoctoral fellow. So that's where I learned all about physical modeling. This is the example here. I'm showing the methane and calcium chloride systems. Our simulator class is able to predict the data very well. Again, methane and MgCl2 is also doing. So we are in the process of developing this simulator with binary salts and then synthetic produced water compositions data we have. So eventually our goal using this class sim process, if you have a produced water composition and the type of hydrate former, we should be able to predict this envelope. Here, this envelope dictates our operating conditions for kinetic experiments. So class T sim defines thermodynamic conditions under which hydrates will form. Essentially tells us the formation is possible. However, thermodynamic stability alone is not sufficient for practical applications. It is necessary, but it's not sufficient. So to implement effectively, we also need to understand how fast the hydrate form, how much water is converted, and how much salt is rejected in the process. So that's where K-Sim comes into picture. It's our kinetic simulator designed to predict hydrate formation rates and evaluate system performance under reactor configurations and operating kinetic data. Here is the example of kinetic data. Here I'm showing the example of gas uptake curve during the hydrate formation in one of our reactor, where we hydrate formation by monitoring the pressure. From this, we can estimate the water recovery. So this is the water recovery data. Water recovery is nothing but is a measure of fresh water extracted from saline water in the hydrate-based desalination process after hydrate decomposition. So water recovery percentage is calculated from the equation here, where FH is the fraction of recoverable hydrates after separation. So separation is a crucial step in the hydrate desalination process. So this figure it represents a comparison of water recovery percentage of different hydrate formers in different salt concentrations. So we are collecting the database to kinetic database also to simulate the clath casing. So hydrate formers having higher water recovery percentage is preferred in this case. Similarly, we can also before and after hydrate formation will provide the salt rejection rate. The salt rejection rate is a measure of salt removal efficiency of the desalination technology we are using. This figure shows the salt rejection percentage of different hydrate formers and different salinities. So obviously we want a hydrate former with a high salt rejection percentage preferred. So cloth casing provides insights into dynamic behavior of the system, how quickly hydrate form, how much water is recovered, and how effectively salts are rejected under specific operating conditions. However, even with optimized kinetics, a process must also be economically viable to move forward to the real-world deployment. So to evaluate this, we transition this into techno-economic analysis. Basically in techno-economic analysis, we want to capture the capital and operating cost and specific energy consumption of this particular desalination process. These steps bridges the technical performance with the economic feasibility, basically. A clathrate hydrate-based desalination process was simulated using Aspen basis. The actual hydrate database, however, we created our own data. We have a data, thermodynamic data and kinetic data available from our laboratory. So we created the hydrate components as special components in Aspen HYSYS and did some simulations. Here, main focus will be in major energy components like a feed water pump, hydrate former compressor, coolant pump, and dissociation produced water and propane compressor, which we use for external refrigeration, heat removal due to the hydrate formation. So the main important parameter here is specific energy consumption and process, and how can we have a lower specific energy consumption. Specific energy consumption is nothing but total energy consumption per meter cube of water we produce. Better we treat, basically. So if you have a low specific energy consumption, that's good for the process for commercializing. So here I'm giving an example of energy consumption of each unit operations was quantified using methane here. Hydrate former is methane. So as you see here, the compressing hydrate former with methane accounted for more than 50% of the total energy demand. So if the key bottleneck is to increase the temperature, increase the pressure of the methane for the hydrate formation conditions. The cost, then we have to change the promoter to to a promoter where we no need to compress that much. So here we tried different promoters. Here I'm showing HFC, hydrofluorocarbon 152A. As you see, the hydrate equilibrium conditions. Again, this is thermodynamic data. So from this data, we determined that okay, HFC 152A can be a viable option here, and then we went through the whole process and for thermodynamics, kinetics, and simulation. As you see here, just the use of HFC 152A reduced the compression load to approximately 16% of the total energy consumption compared to 15%. So the transition from methane to HFC 152A almost resulted 63% decrease in specific energy consumption, so thereby enhancing the feasibility and scalability of hydrate-based desalination. We didn't stop here. We're still looking for how to reduce this compression cost. So the compression energy requirement for HFC 152A can further minimize through recycling. So we started putting a recycling loop in the simulation and reducing its contribution to 0.03%. So we basically eliminated all the compression cost at this moment. If you observe carefully, after reducing the compression cost, major energy consumption is coming from heat removal of a hydrate from hydrate formation, because hydrate formation is an exothermic process, and if you keep on forming the hydrates, the temperature of the reactor will go up. So we have to constantly chill the reactor and remove the heat from the reactor. So that is a major contribution. So we have created these simulations with various hydrate promoters, and we are creating a database again to identify. And we also found that the majority of the major parameters for a hydrate promoter selection is hydration number and enthalpy of formation, because these are like very important factors influencing the energy efficiency in hydrate-based desalination. So, there is two parameters: hydrate for number and enthalpy of hydrate formation. So we combine these two, and we come up with the enthalpy of hydrate formation per mole of water instead of that component. So we come up with one parameter, and we did the simulation theoretical calculations of the specific energy required for heat removal, and then here is the specific energy required for heat removal with the different promoters. So we plotted this enthalpy of formation per mole of water to the SEC. We come up with very nice here. A decrease in just 1 kilojoule per mole in of hydrate formation enthalpy can result almost like 5-fold reduction specific energy consumption. Therefore, selecting the hydrate former with a low enthalpy of formation and a higher hydration number is essential for optimizing the process performance. So instead of randomly selecting the promoters and testing, this kind of consolidated data will give us a picture and then a path forward for future selection of the promoters. And again, these simulations are only conducted with assuming 40% conversion, but is it conversion can be increased, and overall energy can be decreased and to the level that we can commercially implement this process. So the summary of it is produced water is not uniform. It's it is unpredictable, challenging, and growing in volume. So clathrate hydrate based desalination holds transformative aims. To move from possibility to practice, we must simulate and optimize and assess before even we scale. So thermodynamics is central to making this process viable to real world deployment, because the selection of hydrate former, which determines the feasibility and efficiency, and hydrate stability dictates the operating conditions, and predictive phase equilibrium models enable system optimization and process control, basically. And finally, enthalpy of formation directly impacts the energy consumption and economic viability. These are all coming, all the information is coming from thermodynamics. So advancing hydrate-based desalination process from lab to field depends on mastering its thermodynamic foundation. So integrated simulation tools like ClathT and ClathK are critical. They bridge the gap between laboratory insight to the real world deployment. With this, I will thank you again all the people who contributed to this research, and again, thank you for the opportunity. I'm here for to answer any of the questions you have or any feedback.